Okay, so this is chapter 11, problem number 1 for exam 3. If Kc is given, convert to Kp. If Kp is given, convert to Kc. What is Kc and Kp? Well, these are equilibrium constants. Notice that we've got these expressions, these reactions here that are, will go back and forth. For these to go back and forth, there has to be some sort of equilibrium constant. And what we have here is a Kc value and a Kp. So what's the difference? Well, Kc is the equilibrium constant, and that is in terms of concentration, hence the C. So we can also call this in molarity, the big M, moles over liters. So what about Kp? Well, Kp is the same thing, but this time it's in terms of pressure, or otherwise ATM, atmospheres. So obviously these are two different types of equilibrium constant, but how are they related? So we can put these two together in an equation to relate the two. We can determine that we have, that the concentration, the equilibrium constant in terms of pressure can be found by taking the equilibrium constant in terms of concentration, multiplying by RT. Now remember, RT was also used in our ideal gas laws, where R is our universal gas constant, and that's 0.0821. That's going to be atmospheres times liters divided by moles times Kelvin. And then we have our temperature here, that this is measured in Kelvin. So we have to make sure that if we're given something in terms of Celsius or Fahrenheit, we convert it to Kelvin before we can equate this equation. So this is basically what the conversion. And then, of course, at the very end, I don't want to forget this, delta N. Now, what is delta N? Delta N is basically the change of the coefficients of your products subtracted by the coefficients of your reactants. So we'll look at an example. We'll look at part 1 and part 2, and you'll be able to understand how these work. So another thing to keep in mind is with these, we ignore liquids and solids. If we're given a solid or a liquid in our reaction, we don't worry about those. We're looking only at gases. Gases are going to be what we determine for this delta N up here. So these are the parameters. So let's go ahead and start attacking this problem. So what I'm going to do first is I'm going to leave a little note. And one other thing I also want to keep in mind is we want to know if we're going to convert Celsius to Kelvin. Well, 0 degrees Celsius is equivalent to 273 Kelvin. So first and foremost, 0 degrees Celsius is equal to 273 Kelvin. And for every degree Celsius that goes up, we add 1 additional Kelvin. And then again, we can also write the equation Kp is equal to Kc times RT raised to the delta N. So let's look at number 1. Number 1, we have nitrogen gas plus 3 hydrogen gas atoms. And we can see that that's going to go back and forth with 2 ammonia gas atoms or ions. So what do we have here? So we're given a Kc value of 0.5. And we're also given it to 400 degrees Celsius. So what do we know? Well, first of all, we know that Kp is equal to Kc times RT raised to the delta N. So first and foremost, we need to find Kp because we're given Kc. So we can go ahead and replace Kc with 0.50. And also notice that it's unitless. So that's another thing to keep in mind, is that our equilibrium constants are unitless. Okay, now let's go ahead and multiply our R. Now we already know what that is. That's 0.0821 moles or atmosphere times liters divided by moles times Kelvin. And we have 400 degrees Celsius, but remember, we have to add 273 kelvins to it. So that's going to be multiplied by 673 Kelvin. And now what are we going to raise this to? Now remember, I said that the delta N is going to be the coefficients of products minus the sum of the coefficients of products minus the sum of the coefficients of the reactants. So if we look at our products here, I've got a 2 for a coefficient. This is my only product over here. And on the reactant side, I've got a 3 coefficient for my hydrogen gas and a 1 coefficient for my nitrogen gas. So essentially, I've got a 2 minus 4 here. 2 for my products, 4 for my reactants. So that's going to equal -2. So we can say that Kp is equal to 0.50. And I'm going to ignore the units just so I can put the numbers together here. Okay, and then we're going to multiply that by 673, raise that to the -2. Okay, so this is going to be my value for Kp. And then what I calculated this out to be is that it comes out to be 1.6 times 10 to the -4. So this is my Kp value based on these given parameters. Now remember, if I don't have one, I can find the other. Or if I don't have one, I can find it using, the other that it's given. So this is part 1. Okay, now let's go ahead and look at part 2. So let me go ahead and get rid of this. We will now look at part 2. And part 2 is a little different. I want you to pay attention here. So what we have here is we have Na2SO4 times 10H2O. Now notice there's a times. This is not plus. So this is all one whole term or one whole reactant. And it's a solid. So like I said a minute ago, when we're looking at equilibrium constants, we ignore solids and liquids in our equations. So we're not even going to utilize this whenever we go to calculate the delta N. Likewise, on our product side, I've got the Na2SO4 again, and this time it's a solid. So again, I'm going to ignore this whole thing because it's a solid. All I care about are gases. So notice I've got H2O in terms of gas, and I've got 10 of those. So I don't have any other reactants or products that have any that are in gas form other than the H2O. And now in this case, I've given the equilibrium constant and pressure, which is 4.08 times 10 to the -25, and it's at 25 degrees Celsius. So again, using our equation, Kp equals Kc times RT delta N. What do we have? Well, we have our Kp, that's 4.08 times 10 to the -25. That's equal to Kc, we don't know that. Again, R is our universal gas constant. And again, that's going to be the atmospheres times liters divided by moles per Kelvin. And then again, times 25 degrees Celsius, but we need to add 273 Kelvin. So that's going to be times 298 Kelvin. Okay. And what are we going to have up at the top? Remember, it's products subtracted reactants. I have 10 right here. Do I have any other coefficients? I do not, because this is a solid, so we don't care about it. This on the reactant side is only a solid. I don't have any gases, so I don't have any coefficients, so I don't care about that. So all I've got up here is raised to the power 10. That's all my delta N is going to be. So by solving for Kc, I can divide both sides by this value here. And in doing so, I can do it to both ends, and I'll be able to solve for Kc. All right, so Kc is going to equal this value here. And what I managed to get out of that is 5.31 times 10 to the -39. And again, it's unitless. So this is my equilibrium constant for this reaction when it goes back and forth. This is the equilibrium constant that is in terms of concentration. Okay, so this is all we have for this problem. It's a very simple process. You just need to know how to avoid solids and liquids, how to set the equation up, and you're guaranteed to get the answer correct.